In this lesson, we're going to talk about methods to estimate the loading and bulk density of litter, duff, shrubs, and grasses. The first part of the lecture will cover litter and duff. When conducting litter and duff inventories, we are primarily concerned with three variables: the loading, the bulk density, and the depth. In many cases, we will also want to know the cover, but we will not look at methods to estimate cover in this lecture. You can find many methods to do this on the internet and in published literature. Brown presented methods for estimating the depth of litter and duff. However, these methods do not provide a way to get the bulk density or loading. To estimate these variables, we will use other methods. The most straightforward way to estimate loading is to multiply the depth by the bulk density. To estimate the bulk density, there are a few options. You can either take direct measurements in the field, or you can use values from the published literature, such as FCCS, fuel photo guides, or other scientific literature like Brown. First, we will consider estimating fuel loading using published values. The table shown is from Brown 1981. This table lists the bulk density of the litter layer for several common habitat types in the northern Rocky Mountains. Let's consider an example using Brown's table. Assume that we collected litter depths across 25 plots in a ponderosa pine Idaho fescue stand and saw an average litter depth of 1.5 inches. Using this table, we then estimate the bulk density at 22.4 kilograms per meter cubed. Now let's find our total fuel loading in tons per acre. First, convert kilograms per cubic meter into tons per acre inch using standard conversion factors, so by multiplying our value by 0.113. Next, to convert to tons per acre, multiply by 1.5 since our depth was 1.5 inches. We get an estimate of 3.8 tons per acre of litter. Another source for bulk densities is from the Natural Fuel Photo Guides. You can access these online at the website listed here. You have two options when using the photo guides to estimate fuel loading. The first is to use a loading value from the guides which best matches your conditions. The second is to calculate the bulk density from the guide and use your depth measurements from the field. Let's try an example using the photo guides. Suppose we have sampled a lodgepole pine forest with an average litter depth of 0.7 inches and a duff depth of 1 inch. You can use the photo guides to search for forests that meet your constraints. Here I have chosen a lodgepole pine forest and entered my litter and duff depths. After reviewing the photo guides, we see that guide LP03 has a reported litter depth of 0.5 inches and a duff depth of 0.9 inches, which is very close to ours. Then, we could simply use the values from this model and report our loading as 2.4 tons per acre of litter and 10.3 tons per acre of duff. Note that FCCS is set up similarly, so the process to obtain this information is the same. Another option that I mentioned is to calculate the bulk density for the photo guide or use the estimates of bulk density from our Brown's transects. I will not go over these calculations here, but they are similar to the previous calculation example. Bulk density can be directly measured using methods developed by the FURA group of the Pacific Northwest Research Station, led by Dr. Roger Ottmar. The method that Otmar uses is very intensive, requiring multiple measurements of depth within a small area and the removal of material for drying and weighing. The picture on the slide shows the schematic. In this method, you place 12 nails at the top of the litter within a square foot metal frame, then remove all the material into a bag and measure the amount of nail revealed. The material is then taken, dried, and weighed. The combination of height, width, length, and weight gives you all the required elements to calculate the density. Now let's move on to the herbaceous fuels. Next, we will discuss sampling the bulk density of herbaceous fuels. Again, there are several methods that we can use, such as natural fuel photo guides, clipping and weighing, or relative weight estimates. The most straightforward and common method used for understory vegetation is the clipping and weighing method. To use this method, first measure the mean height. Then, clip all vegetation within a known area, dry the samples, and calculate the loading. To get the bulk density, divide the loading by the height of the plants. Another common herbaceous fuel loading method is to use a relative weight estimate technique. In this method, choose 4 to 5 small, so about 4 to 5 meter, plots to sample. Estimate the plot with the most biomass. Then, estimate the fraction of herbaceous biomass on the remaining plots based on the plot with the most. Next, clip and weigh the plot with the maximum biomass and use the weight to estimate the weights of the remaining plots. The proportions of the plots are estimated in the field. For an example of this method, assume we are still working in a ponderosa pine Idaho fescue stand. We have collected 4 understory plots labeled 1 through 4. We estimated plot 2 to have the most biomass. The proportion of 1, 3, and 4 were estimated as 50%, 80%, and 90%. If the clipped plot had 159 pounds per acre, we can estimate the biomass of the other plots as 79.5, 127.2, and 143.1 pounds per acre. We can then average these together to get a site average of 127.2 pounds per acre. When using this method in a fuels inventory, you will often use 4 to 5 plots per 1 overstory plot. You will average the 4 to 5 understory plots for each overstory plot. Finally, you will calculate an average based on the average of each overstory plot. For example, let's say we collect our canopy fuels data on 1/10 acre plot with 4 half-meter understory plots. If we collect 10 overstory plots, we will collect 4 understory plots per overstory plot for a total of 40 understory plots. You should not take an average of all 40 understory plots as a whole, but instead average each of the 4 understory plots for every overstory plot. Then take an average of all 10 overstory plots. Note our sample size is 10, not 40. The advantages of using relative weight estimate are that it requires little training, it is not affected by moisture, and it does not require the user to check estimates against actual weights. The disadvantages of this method are that all plots must be easily observable, clipping and weighing of 1 out of every 4 or 5 plots is still required, and the accuracy of the method is not known. Another option is to use statistical correlations to estimate herbaceous fuel loadings. High correlations have been found between weight per unit area and cover and height in rangelands. However, in forest ecosystems, this relationship is not as strong. The major drawback to using statistical correlations is that if the area you are working in does not have a specific correlation already explained, then the accuracy of the method may not be known. Next, we will consider methods to estimate the bulk density of herbaceous vegetation. Remember from our previous lectures that bulk density can be obtained by dividing the weight per unit area by a depth. We can obtain the height and loading methods from many combinations of sources. For example, we can use the photo load method and photo guides to obtain loading and height estimates. Another option is to measure the height and simply obtain the loadings from these guides. Yet another option is measure height and loading from clipping and weighing. Now let's move on to talk about shrubs. Both destructive methods and non-destructive methods may be used to measure shrubs. Destructive methods are usually not used because they are very time-consuming and may have long-term impacts on the site. However, in some cases where destructive sampling is done, there are few options. You may choose to sample the whole plant, or you may choose to sample some subset of the fuels, such as the 1-hour fuels. Less destructive methods include the reference unit method, double sampling, and using a statistical model based on crown volume or basal diameter. The reference unit method and double sampling method still require some clipping and weighing. The reference unit method relies on sampling a small unit of the plant and then scaling this unit up to the whole plant. Generally speaking, the reference unit is about 10 to 20% of the plant by weight. To use this reference unit method, first you clip the reference area and estimate the number of reference units on the entire plant. You then dry and weigh the sample, and then multiply the weight by the number of reference units. This method is used to estimate the number of shrubs per unit area and multiply up. In many cases, you may have to use this method on a range of plant sizes and species to get a stand or plot level data. Here is an example of the reference method. In this example, we estimated that there were 8 sample units. We then clipped and weighed one of the reference units. We found the unit to have a weight of 2,000 grams. Next, we multiply this weight by the 8 sample units and we get 16 kilograms. Another approach is to use double sampling, relative weight method. We covered this method when we talked about herbaceous fuel loading, and the same methods can be used for shrub loadings. However, these methods can be difficult to conduct on shrubs. One of the major challenges when using this method is deciding upon the plants of the plant to clip. For example, we could clip only foliage, the whole plant, or the foliage and 1-hour fuels. The estimates are on a plant basis, so the number of plants per unit area will have to be estimated or measured to obtain a stand or plot level estimate. Now let's move on to talk about using statistical methods to estimate shrub loading. As an example of this methodology, we will look at some work done by Brown. This work built statistical relationships for 25 northern Rocky Mountain shrub species. These were divided into 3 groups based on height. These equations also allow for the prediction of leaf-only values or total above ground weight. In this paper, the equations have the form of the natural log of the weight is equal to a plus b times the natural log of the basal diameter. The weight is predicted in grams. A and B are species-specific constants. This table shows the number of samples used in the development of the equations, the range of those samples, and the A and B variables for both leaf-only and total weight. Here's an example for snowberry. Assume we measured a snowberry bush which has a diameter of 0.9 centimeters. First, notice that the diameter is in the range of those sampled in the brown paper, from the table on the previous page. Now we can look up the A and B parameters in the table. We see that these values for snowberry as 3.49 and 2.285. Let's start by writing out the full equation and substituting in the A and B values. We then work through the mathematics and get a final value of 25.79 grams. For those of you who do not remember to get rid of the natural log from the left side of the equation, we use the constant e to the value on the right. In Excel, this function is exp in parentheses value. Now let's go over an example for a stand. In this example, we conducted an inventory and found there to be 250 snowberry plants per acre with a 0.9 centimeter diameter, 150 with 1.1 centimeter diameter, and 350 with a 0.5 centimeter diameter. First thing we need to do is calculate the weight of each diameter class. Next, we need to multiply the weight by the number of plants. Lastly, we add up the total weights to get a site loading. We could also use biomass volume estimates as an alternative. In this method, you estimate the volume of the plant and then apply a ratio of dry weight to volume in order to estimate the loading. This is simply like going from a bulk density to a loading where we know the volume. In this table from Bentley et al., you can see the average ratio of dry weight to volume for 4 common shrubs. We could work through the calculations for snowberry again if we had estimates of the volume. Bentley et al. Simplified this process by classifying all vegetation based on their diameter and height. You could use this table to estimate crown, class, and volume. Once you have estimated the crown class, you can assign each class a volume value. Here is a sample of what the full table would look like in a sample stand. Take a few minutes to look it over. I would now like to take a few minutes and return to estimating bulk density. In the most basic sense, we can estimate the bulk density by dividing a loading by an estimate of crown depth or height. These loading values can come from any of the estimates we have talked about and some form of height or canopy depth estimate. To mathematically model fire behavior, you must enter an estimate bulk density for the fuel bed. This surface fuel bed is a collection of live and dead fuels of various sizes. One way to estimate this is to use bulk density values reported in brown. These estimates are for several dominant fuel groups in the northern Rocky Mountains. The classes were developed based on the dominant understory and overstory, and bulk densities are reported for the dominant fuel groups. Here is one of the examples from Brown. When attempting to create custom fuel beds for the mathematical prediction of fire behavior, we can utilize data such as this to help estimate the fuel bed bulk density instead of collecting lots of data.